All right, so we're starting off our unit on analytic trigonometry. So we're going to be solving equations and working with proofs and things like that. So first we're going to talk about using trig inverses to solve, and we are no longer going to be working with inverse functions. So before, when we used inverses, we had functions, and so that meant that we had limited answers that we could have. We had to, for cos inverse, we had to look in quadrants 1 and 2. For sine and tan inverse, we had to look at quadrants 1 and 4. Now that we're dealing with using inverses to solve, we're actually going to look at all of the quadrants. So I like to relate this back to looking at a square root graph. If we are talking about a square root graph as a function, then that means that my graph has to pass the vertical line test. And so a normal square root graph looks like this. I could also have a square root graph that's a function if I said y equals negative square root of x. So both of these are considered to be functions. And that's because based on the pieces that I have, they pass the vertical line test. If I wanted to look at an equation that was not a function where I just used an inverse to solve, that would mean I was looking at something like y squared equals x, and I wanted to solve for y to be able to graph my equation. So if I square root each of these sides, then y equals plus or minus the square root of x. And so what that means is that I have both pieces of the graph at the same time. So if they originally gave me an equation y squared equals x, what they gave me was not a function, because when I solve for y, I have to graph both of those, and it doesn't pass the vertical line test. So here's an example of a function. Here's an example of an equation that I can graph, but it's not a function. So what we did last unit is we were dealing with trig functions, inverse trig functions, where we had limited numbers of answers. Here, it's kind of like when you take a square root and you have to take a plus minus. So if the original problem has the inverse notation in it, then you are specified either to like positive square root x or negative square root x, or in the case of trig, you are specified to which quadrant you can look at. If you are square rooting to solve the problem yourself, you yourself are doing the inverse of the operation, then you have all of the possible solutions. So you'd have the plus or minus. Or in the case of trig, if you yourself are doing the inverse, then you would look at the entire unit circle. All right, so we are going to go ahead and start off solving some of these problems so that you can see what I'm talking about. So we are going to start off by solving the equation 2 sine theta minus 1 equals 0. And when we solve equations, we're always going to have to look at the instructions to see how many of the solutions they want us to have, because there are infinitely many. So if they give us this equation and they say find all solutions, then that means they want every single possible solution for the problem. So I'm going to go ahead and I'm going to start moving things away from theta so I can get theta by itself. So I'm going to add 1 to the right side. That gives me that 2 sine theta equals 1. Then I'll go ahead and divide the 2 to the other side. So that means that sine theta equals 1/2. And then to undo sine, I do not divide by sine, because dividing by sine is like doing cosecant, and cosecant doesn't undo it, it will take the theta with it. So dividing by sine would be like rewriting the problem as as writing cosecant theta equals 2. You didn't actually solve for theta, you just changed it to another type of problem. So if I undo sine, I do not divide by sine. I write sine inverse in front of it. So sine inverse will actually cancel out the sine. So sine inverse of sine, those cancel. I get theta equals sine inverse of 1/2. So if the original problem looked like this, if that's all they said solve for theta and they gave you that original problem, then you would specifically be looking in quadrants 1 and 4. But since we did all the work to get there, that means that we have to look at every single possible solution. And so now we are going to look at our entire unit circle, and we're going to look on the whole unit circle to see where the y coordinates are 1/2. And I can see it happens in 2 places. It happens right here at pi 6, and it happens over here at 5 pi 6. So I'm going to write that there are 2 answers on the unit circle. Theta equals pi over 6 and 5 pi over 6. Now, if they had given to us in the original problem that we were only supposed to find the solutions between 0 and 2 pi, then we would be done, because these are the solutions between 0 and 2 pi. But we have to keep in mind that we have all those coterminal angles, that I can add a full circle and add a full circle and subtract a full circle and add a full circle and get another angle that's in the exact same spot, but is written bigger or smaller. So now I have to write plus 2 pi k. So what this means is that k is a multiple of 2 pi, so I can add or subtract 2 pi as many times as I want to find other solutions. And so plus 2 pi k for this one as well. So these are the solutions on the unit circle. This is what I write to say that you can continue to add or subtract to get more solutions. So that is my answer for this problem if I want all possible solutions, every single solution you could ever possibly have for this problem. Okay, we're going to do the exact same equation. So 2 sine theta minus 1 equals 0. And now we're going to specify that theta is in between 2 pi and negative 2 pi. So I know that the solution process would be the same, so I still know that theta is going to equal sine inverse of 1/2. And I know that if I was to look at the unit circle, I would get theta equals pi over 6 and theta equals 5 pi over 6. But now what I need to do, those were the answers between 0 and 2 pi. Now I need the answers between negative 2 pi and 0. So I'm going to take each of these fractions and I'm going to subtract 2 pi off of them. So if I have pi over 6 and I'm subtracting off 2 pi, then I'm taking pi over 6 and I'm subtracting 12/6. And so my first answer between negative 2 pi and 0 would be negative 11 pi over 6. To get the second solution between negative 2 pi and 0, I would have to take this second one, 5 pi over 6, and subtract off 2 pi. So 5 pi over 6 minus 12 pi over 6. 5 minus 12 is negative 7. And so we would have 4 solutions between negative 2 pi and positive 2 pi. So for an entire period of the graph, right, so the period of a sine function is 2 pi, we're going to have 2 answers. If we have 2 periods of the graph, we're going to have 4 answers. Okay, let's continue with another example. So for this one, we have sine x plus the square root of 2 equals negative sine of x. And so to solve this problem, I need my signs because sine of x represents my unknown value, my variable. So I want the signs to be on the same side. So I'm going to go ahead and subtract sine x over and subtract sine x to the right side. So I get the square root of 2. And if I have a negative sine x and another negative sine x, then I have 2 negative sine x's. So it's negative 2 sine x. I'll go ahead and divide by negative 2. So I've got negative square root 2 over 2 equals sine of x. And then I'm going to go ahead and get the x all alone by doing the inverse of sine. So that gives me that x equals sine inverse of negative root 2 over 2. So I'm trying to find on the unit circle all the places where the y-coordinate is negative root 2 over 2. And so I can see that that's here at 7 pi fourths and 5 pi fourths. Oh, I forgot to finish my instructions. Okay, so back up here. Whenever you solve an equation, they always have to specify how many answers they want. So the instructions on here are going to say on the interval 0 to 2 pi. So the reason they wrote it like this, if you guys recall, 0 and 2 pi are coterminal angles. They're in the same spot. So when they write it like this, they're saying that if that's the spot you're looking at, 0 is not the answer, 2 pi is the answer. So just be careful to watch out for that if they put it on an interval to see which one you can equal. So basically what they were saying is only look for the answers that are on the unit circle and then you're done. And so that problem is finished. Okay. Next problem, we're going to look at a tan example. So this is 3 tan squared x minus 1 equals 0, and we are looking for all solutions. Okay, so here, I'm going to go ahead and rewrite this problem. Tan squared x is mathematician kind of notation. It means that tan x is being squared, and they were just too lazy to write their parentheses. So I'm going to rewrite this problem as 3 tan x is being squared minus 1. Okay, so I'm going to start to move things away from x. I'll add 1 to the other side. And then I'll go ahead and divide the 3 over. And then I need to get rid of that exponent of 2, so I'm going to go ahead and square root each side. And when I square root, I do have that plus minus in the front of it. And before I can move on with the problem, I need to fix this right here. So whenever you have square roots over a fraction like that, you can split it apart. Square root of 1 on the top, square root of 3 on the bottom. And the square root of 1 is just 1. So I've got 1 over square root 3, which we know is not proper notation, but I'm actually going to go ahead and leave it like that for now because this is not our final answer, and it's going to be a little bit easier for us to recognize what it is on the unit circle if we leave it like that. So I'm going to say tan x equals plus or minus 1 over square root of 3. And since I have a plus or minus, it's kind of like I'm solving two different equations here. And so I'm going to go ahead and branch off and do 2. So I'm going to say tan x equals positive 1 over root 3, tan x equals negative 1 over root 3. And so now I'm looking at my unit circle for where y divided by x is 1 over root 3. So I know the two places where tan is positive is quadrant 1 and quadrant 3. So I know that's where those answers are going to fall. So y divided by x is 1 over root 3. I can see that that's going to be pi over 6. And I can see over here that 1 over root 3, it would simplify to positive, but it's two negatives, is 7 pi over 6. And what you'll notice is that these are exactly, they're on a straight line. So these are pi away from each other. So if I was to look at all my answers, that would be this. It would be pi over 6, 7 pi over 6, 13 pi over 6, 19 pi over 6. They would just, all the answers would differ by 1 pi. And that's a special trick about tangent, is that the answers repeat every pi, or if we had looked at a tangent graph, we would have seen that the tangent graph has a period of 1 pi instead of 2 pi, like sine and cosine. So for these, when we write all solutions, instead of saying pi 6 plus 2 pi and 7 pi 6 plus 2 pi, we're just going to write this one, and we're going to say plus pi. So every multiple of pi is actually going to give us another answer. So here, I'll go ahead and finish writing the problem because I skipped that step. So x equals tan inverse of 1 over root 3. And so x equals pi over 6 plus pi k. So the answers repeat in multiples of pi. Okay, we're going to do the same thing on the other side. I'll go ahead and do my notation first this time. So x equals tan inverse of negative 1 over square root 3. And so I'm going to look at my unit circle. I knew the two places where tangent is negative is in quadrant 2 and 4. And so I'm looking for y divided by x. That's going to be 1 over root 3, which is here and here. And again, we can see because it's a tangent inverse that the answers repeat every pi. So 5 pi over 6 and 11 pi over 6. So my first answer is 5 pi over 6, then 11 pi over 6, then 17 pi over 6, then 23 pi over 6, then 29. So instead of writing that I have two different answers that repeat every 2 pi, I can say I have one answer that repeats every pi, because you just have to add half a circle to it to get the next answer. So I'm going to say that x equals 5 pi over 6 plus pi k. And so those two solutions represent every possible solution to that equation.